Yeah, so today I'm going to talk about not the business value, but I'm going to talk about pure fun that you want to do at home. And it's really cool to do stuff that you can show and then that you have in your hand, and you can feel it. It's not just an app on the phone. So I'd like to start with the video. So there is no sound, but these are actually LED matrices. Yeah, you can watch the whole video yourself. So this is fun. This looks fun. Yeah. And actually, it's not written in Erlang yet. So that's only just LED matrix and then a microcontroller as hardware. But my point is, it might as well have been written in Erlang. You saw it, it's network topology, they choose leaders, and you communicate, you do message passing, do that, rotate the arrow in that direction. And you can scale it, you can just add more matrices and it's doing the same thing. And that's what my feeling is about controlling hardware with Erlang. It feels very natural. You have hardware, it's almost always in different states, and you can model that very naturally in Erlang. And you have recursion, you're just doing something and then maybe the state changes and you're going to another state, and you communicate, you send messages, you receive messages. So do that in Erlang. It's fun. And you can do anything you want. So if you want to check this out. So what did I do then? So if that wasn't written in Erlang, what did I do? So I built Adafruit projects because I saw that there is something I want to do. I didn't know so much about hardware, and if you ask my boyfriend, he'll say I don't know anything about hardware. But this is very easy to do because you get the do-it-yourself kit and you just assemble it and you just run the software that comes along with it. And you get source code written in Python mostly, and it's very similar to Erlang. So that was like my starting point. I just built something that somebody else had designed so that I need not worry about anything. But of course, I didn't want to program in Python. So I made it in Erlang instead. And here I did a LED matrix myself. That's a sinus curve. And that's the LED matrix is extra fun because it's so visual. You do something that shows. You can do pretty patterns. And it's easy. And I also did something. Here is a radio-controlled car. And you think that must be very difficult to do that. But actually this was very simple, because you don't actually do the radio interface. You don't meddle with that. You just hack yourself into the remote control. And when you opened the remote control, I didn't think it was true. It's the joystick. It was a plastic thing. It just pushes down 2 buttons. So you just have digital zeros and ones that, oh, now you right, left, right. So this is what it looks like. And then you have these test points that they use to test the hardware if it's functioning all right. And you can just hack yourself in there and just send the zeros and ones from the Raspberry Pi. And it's so easy. I didn't think it was possible, but it's very easy to do. It's very fast. You can do that one afternoon if you have nothing better to do. And there is so much to choose from on Adafruit and other sites. There are so many sites out there that show you projects with a Raspberry Pi. You can just choose whatever you want. Like this one was an AD converter, and when you have sensors that give analog values, you need an AD converter to get the digital values. And this is actually a distance sensor that was not on Adafruit, but it's easy to just add it because you have the code for the AD converter, so you know how to read values, and the distance sensor is just feeding the values. So there's so much to choose from, like a dog collar with a GPS, so you can track your dog's movement, an FM radio, an arcade thing. So my recommendation is just to choose something and just to start building it, because it's very fun. And once you have something, it's easy to do the next step, that you change something and you add your own little twist. Maybe you don't want to have an FM radio there, you want to have something else, then you just change it. So, why use Erlang? And I know this is the worst thing to say at conferences, but this was my main reason, simply because it's possible. I love Erlang. I learned it in 2006, I think. And I didn't really feel comfortable with Python. And I thought, no, I want to see if it's possible to do it in Erlang. And this was my main reason, as I said. It's okay, when you have some LEDs you're controlling, this is not very difficult, but as soon as you have a bigger application like this, it's very easy to do it in Erlang, because then you have the design that helps you. You have the modules and you know how to model it in Erlang. So for me, the code writes itself. So it's when you build bigger systems that you want to have Erlang, where you get the benefit of Erlang. And like I said, I think it's ideal for talking to hardware, because the hardware is stateful, and you need the fault tolerance, you need the communication, sending values back and forth. And you want to extend your code later on. So if you decide that, oh, I want to make it connected, I want to connect it to a big network, then you can do it. It's simple with Erlang once you have laid the ground. And then why not use Erlang when it's a Raspberry Pi? I know there have been some discussions about embedded that, yeah, not all platforms are suitable for running Erlang. Like microcontrollers, you don't have enough memory. You can't run an Erlang VM simply. But a Raspberry Pi, this is actually sort of a little computer. It has everything, and the OS you get, it's a full Linux distribution. You have all packages you want available. So why not? And the thing with the Raspberry Pi is that it has these GPIO pins, so it's very easy to connect hardware. So where does Erlang fit into this? When you program such an LCD display, what you get from Adafruit is, in the Adafruit, they have a GitHub repository. You download the software, and it's like a very thin Python application, and then it's a driver code for the LCD display that just sets different registers and so on. And that's easy to change. You can, the Python application here, I don't know if you can see it, it sets, it prints out the IP address on the LCD display. And it's a very simple thing to just change what you want to print. And then, oh, I did this. Then you can make it your own. It's very important to make it your own. You must decide what do you want to do. And then there are Python libs that you need to install beforehand. And it says in the installation instructions you have to download this and this and this. And these give you access to the GPIO pins and so on. But also Python needs something beneath, and this is simply calling the OS. So it's the Linux kernel that's doing all the communication to the GPIO pins. And you have a few different technologies. You have memory mapping. The Linux kernel, they expose files that you can just write to file a value, and then it goes out to the GPIO pin. And then you have command line tools. So even if you don't have an application on top, you can test your hardware. Yeah, so what do? You just change it. You just use Erlang instead. Yes, that's a piece of cake. So what I did was I Googled I2C, because like I said, I don't know anything about hardware. So I2C is basically a bus that defines how to talk to a hardware. So you have two pins. You have one clock pin and one data pin. And there are simple I2C devices, and there are more advanced I2C devices. The more advanced I2C devices are called SM bus, and they have sort of like an addressing system, yet that you have a hardware address, and then you have a register address, and then you just read and write to and from registers on the hardware. So what I did was I took some C code that I Googled. Google is your friend. There is so much code out there. And then I wrote an if, because that was easiest and fastest for me. And I thought it was okay, because yeah, the C code that's underneath there, it's from IOCTL, and I thought it was well tested, and you get Unix error codes back if it doesn't work. So I thought that's okay. I can live with that. It maybe crash, but it actually doesn't crash that much. It's pretty stable. So then the C code calls a Linux kernel module, and I call the Erlang code. There I have like open this address on the I2C bus. I can read registers, write registers. Then I can just take the datasheet that tells me which registers I should read and write, and then I can test the hardware manually. So it's not that hard to do. Yeah, and for this I was lazy. I used the C API in the Linux kernel because I didn't want to do the implementation of the SMBus read and write myself. There is already an implementation, and I just took it, and this is so simple. It's almost ridiculous. So the code there it's very little code. It's very thin. And then, bang, I'm in Erlang. I don't need to use C. I don't need to use Python. Yeah. And of course, you can reuse my code if you want to do something yourself. SPI support, I didn't do it yet. Yes, that's my next thing. Of course, there are other libraries. This WPI, it uses the wiring pi library, so it goes one step further. It has the limit a little higher, so it uses a C library that does all the hardware stuff and just calls this, and there is the Erlang actual library for embedded. I didn't look at it that much because I was interested of doing the code myself. And you can do that too. It's your choice. So this is actually very easy. It's so easy. Yeah. So of course, everybody knows that you should work test-driven. So this driver for the AD converter that I wrote, it's actually very well tested. It has unit tests with MacGyver and Proper. Proper is the free version of QuickCheck, roughly. And what I was planning on doing was system testing with common test. I didn't actually get that far. But this also helps you if you don't have the hardware available yet. So you have your application here, and you want to test it with common test. And how do you do that? Well, my thought was that I should write simulators. And those simulators, those are really easy to write in Erlang, because they are just, yeah, I'm faking that I'm setting this register, and I'm faking that this is happening. And then what you do is you send messages to the test case that the test case can subscribe, and then you say, oh, now I have set this register value. And this is very good because you can test all the way down. You can test everything that happens. And you don't actually need a hardware at all. So this was my plan. I didn't actually do this, but it's easier than it sounds. So testing is good for you. I'd just like to show you one MacGyver and one proper example. So the NIF that I wrote, that's not actually testable, but above that, the driver for the AD converter wrote a few tests for that. So he just tests that you use the I2C bus, that you open it when you init the driver, and when you terminate the driver, it should close the bus. And proper, how many of you know quick check? Oh, that's quite a bunch. So proper or quick check, the point is that you don't always know what test cases you want to write. You want to test properties of the code. And this tests some properties of the driver lib. That's, yeah, I wrote that for encoding and decoding data. So I abstracted the bit fipling because that's a very advanced AD converter. It turned out that it was too advanced for the purpose. But there are a lot of registers and configuration registers, so the data sheet has enormous amounts of tables. When you set this bit, then this will happen. When you set this bit, then this will happen. And of course, you want to abstract that in software. So you say that you have status bit, and then you can test that every time you set the status bit on any bit pattern, the status bit should be set afterwards, of course. So then I thought, oh, I want to build something on my own. Not now I followed someone else's instruction in design, but I really want to do something myself. And I thought, wouldn't it be cool to have the time circuit from Back to the Future? Yeah, and I built it, and it actually works. So I changed the design a little bit. I thought, I don't want it just to have as a decoration, but I wanted to do something. So what I did was to have this destination time, and then I have the current time, and then this here is a countdown clock. So it counts down to any event. So this here, Erlang conference yesterday. So the 2nd of May, it was 38 days, 21 hours, 51 minutes, and 47 seconds left to the red date. So how hard can it be? Well, it turned out it was as easy as I imagined. Of course, it took a lot of work and it took a lot of time, and I needed to learn a lot on hardware design. I didn't do any CADing before, but it was possible. The routing was very time-consuming in Eagle. For those of you who don't know, Eagle is a CAD software, so that's used to do the hardware design so that you can actually make these circuit boards that are behind here. So I designed them, and then I let them print it. I ordered them in Germany. So they printed from my design. Yeah, and that was the most difficult thing to do, to learn how to draw that. But nowadays you have so advanced tools, so yeah, it was okay. And then these these components here, those are pretty small, so these had to be surface mounted, and I couldn't do that myself, but I think I could do it if I just have a lot of time. So what I needed was some displays for the numbers and alphanumeric displays for the month. Micro USB for the power, and then I have this display driver chip. And my point was that if you're using Erlang, maybe you cannot do the hardware like with microcontrollers and run Erlang on that. But you don't need to. I chose this display driver because it does all the work for me. So the hardware is actually very simple. So those who designed this hardware, they did all the job for me. So I have a dedicated IC that does all the display driver stuff, and I just write registers and read registers. And that's very easy to do from Erlang. You just tell it, now you can write an 8 on that display, and then it does it. So the hardware design is simple. Keep it simple, stupid. So maybe this doesn't look that simple to you, but it's actually very simple. It's this display driver does all the work, and then you have some LEDs, because of course you want to have blinking LEDs between the hour and the minute, and you have some resistors, some capacitors, and that's all. And actually, that was written in the data sheet to the IC. It was written, here you need a capacitor, 22 picofarads, and then you just take it. I didn't need to think about the hardware design. It just created itself. I just wanted to add those displays. Yeah, and simple is a relative term. This IC is very small, and there are many output lines here to all the different displays. So it was very narrow here. But that just took time. It was not difficult for me, even if I haven't done any hardware design before. So when you put it together, of course you must test the hardware, that you have mounted it correctly and that there is a connection everywhere. So this display driver, it had a display test mode. So you just write a 1 to register 7, and then it just turns on all the displays. So then you can see that it's working. And I actually didn't access this hardware with anything other than Erlang. So it's very easy. I just needed my ITC primitives, and I just say open this address and then write a 1 to register 7, and then turn on all the displays, and then, oh yeah, it's working. And this is so fun. When you do something, you can actually touch and see, and yeah, it's working. So of course that was not very advanced, so then I needed to do all the implementation that showed the date and time, and that was a little bit harder than I expected. So I just threw it together to make it work. But there were some thoughts. So I have a main program that sets the date and time. And then it changes the destination time just to see that this counts down to 0. And I have one yen server for every row here. So these are separate modules. They are functioning independently from each other. And then they use some things in this time circuit lib. Of course, this library should be a driver, and I will refactor it, but this is the main structure. And what it does is the gen servers are periodically sending themselves messages, like toggle LEDs, checking time. And this is in a higher frequency than the actual update. So this is done more than, that's 100 milliseconds between each message here, because Erlang is a soft real-time system, and I have no guarantee that if I say send this in 1 second, that it will be 1 second. So actually this is running on a higher frequency, and then it just checks, is it the next second yet? And when it is, it updates the display. And when you change the destination time, then actually the destination time sends it to the countdown clock. So the countdown clock can calculate any difference. And this works. Yeah. So 5 minutes, yeah. So what about communication? Erlang is good at communication. And I work at a company called Cybercom. And their mantra is connectivity, so boosting your performance in a connected world. So I had to make this connected somehow. So what did I do? I made the system distributed just for fun, just to show that it's possible. And it was very simple. I just took this countdown clock, this last row, and I I connected it to another Pi, and I just ran the software on another Pi, on another node, on another Erlang node, and I just use RPC call just to communicate between the two nodes, and that was all. It's so simple, and in a connected world, Erlang rules. So as soon as you build bigger systems and you do connected systems, then it's really very easy to get value for the money when you use Erlang. Okay, I don't think I have time to talk about. Yeah, so then I thought, yeah, if I want to have hardware, then I want to have Bluetooth. So I Googled, is there Bluetooth support for Erlang? And I didn't find anything. I found an empty GitHub repo. I don't know if you know more than me, but I didn't find anything. So I would like to send binaries the Erlang way. I don't want to care that I'm using Bluetooth instead of TCP, but I would like to use Bluetooth to save energy. So if it doesn't exist, write it yourself. So then I wrote an interface to Bluez, and Bluez provides the Bluetooth stack in Linux, and that's actually very easy. So I created RFCOM sockets, and they work just like TCP sockets, and it's really the same thing. The difficult thing was that the cards must be put in scan mode, and it was very difficult to set it up and get it working, but when it worked, it was so easy. Yeah, and also, like with TCP, you have no guarantee that when you send packets and then you read them on the other side, you can't know whether there's one packet that has arrived or 3 packets, and when you read it, you will read all 3 packets at the same time. So what I discovered was that when you have binaries that are concatenated in Erlang, then Erlang will just read the first binary from that. So I had to do sort of like a manual thing to check how many bytes did I receive. So then I know it's not the last binary, then I just take the first binary and then take the second and the third and so on. So this was my code. So when I wrote the socket code, this one is actually the same as for TCP. You create a server, you bind a socket, you listen to the socket, and you have an acceptor. And in the client side, you connect. So this was actually just a proof of concept that it works. So I'd like to develop this further, but I would like all of you to help. Yeah, and I'd like to have the same support that inet has. So yeah, a simple protocol like just header with the length and the binary contents, and yeah. Maybe make use of Bluetooth services because they have their own concept. You can scan for services and then you can connect. And that card setup you need to do in the beginning. And of course it should be rewritten as an Erlang port, it shouldn't be an if. And maybe support for Windows, but I heard that's pretty awkward. Yeah, so let me know if you're interested in helping this.
So, do we have some questions?
So you said it was very easy to write the NIF. How much hours did you spend, or how long did it really take you?
I didn't count the hours, but
can you give like a rough estimate?
Yeah, well, I don't know, 5 hours maybe for that. It wasn't that much. I mean, we're all time optimists. We think it will take like 10 minutes, but I think 5 hours is not that much anyway. It could take weeks and months to do it in C for me. Do it like the whole application in C for me, so it was not that difficult.
Great. More questions? Well, okay, I just want to thank you. I mean, it's very fun to see that you can portray such, at least for me, very uncommon aspect of programming Erlang and emphasis the simplicity. That's fun to see. So again, a warm round of applause, and remember to vote.